The next chapter is momentum. In this chapter we will learn about the idea of momentum, modeling collisions, understanding collisions, explosions and crash landings. Now if it's an explosion, the total momentum before the explosion is 0, and according to the principle of conservation of momentum, total momentum before equals total momentum after. We will learn these details. So after the explosion also the total momentum is 0. We will see collision in 2 dimensions. In the O-level class you all may have learned collisions in 1 dimension. You would have seen momentum. Those students who did the Edexcel are familiar with momentum. Cambridge students would not have had the momentum lesson in their syllabus for O-levels. Anyway, we will see momentum in 1 dimension as well as momentum in 2 dimensions. So in the O-level class you all would not have learned momentum in 2 dimensions. Momentum and Newton's laws. I have also uploaded videos explaining the Newton's laws, and here we will specifically see the Newton's second law, because the Newton's second law has the change in momentum, understanding motion, and finally the summary. So let's see again what we will learn in this chapter. Define linear momentum. State and apply the principle of conservation of momentum to collisions in 1 and 2 dimensions. So we have 2 dimensions also now. If you take higher levels of physics, you will have 3 dimensions also. Relate force to rate of change of momentum. Now if you learn the Newton's laws, you know that the Newton's second law is saying that the resultant force is equal to the rate of change of momentum. Discuss energy changes in perfectly elastic and inelastic collisions. We will see in an elastic collision the momentum is conserved. In any collision the momentum is conserved, whether it's elastic or inelastic. Always, in any case, the momentum is conserved. If it's an elastic collision, the kinetic energy is conserved. If it's an inelastic collision, the kinetic energy is not conserved. So if also we will see the details that if it's an elastic collision, the relative speed of approach equals the relative speed of separation. Otherwise, they are not equal. Okay, so we will see. To improve the safety of cars, the motion of a car during a crash must be understood and the forces on the driver minimized. In this way, safer cars have been developed and many lives have been saved. In this chapter, we will explore how the idea of momentum can allow us to predict how objects move after colliding, interacting with each other. We will also see how Newton's laws of motion can be expressed in terms of momentum. Okay, so here you can see the idea of momentum. Here are some examples of situations involving collisions. So you can go through this. And there are some examples here. I will go through the important points. Okay, so we have springy collisions and sticky collisions. Now if the 2 objects stick together, then the momentum is not the kinetic energy is not conserved, so clearly it is an inelastic if the 2 objects stick together, we say stick together or coalesce. If they coalesce, so if they stick together, another word that is used is couple. So if they couple or if they stick together, then after the collision, then it is a perfectly inelastic collision. It's an inelastic collision. And this equation is important, and also we can use this as the definition. You should know this. See, defining linear momentum, and we have this. Now you should know this also. Conservation of momentum states that within a closed system, the total momentum in any direction is constant. The principle of conservation of momentum can also be expressed as follows. For a closed system in any direction, total momentum of objects before collision equal total momentum of objects after collision. So a lot of students forget to write this first part. For a closed system in any direction, so then you can say this. So if you just write total momentum of objects before equals after, then that is not very complete. You have to also say this in a closed system. See, we can also state it like this: within a closed system, the total momentum in any direction is conserved. This is the principle of conservation of momentum. This is also another way of saying the same thing, the principle of conservation of momentum. Okay, now to understand this better, we will go through some examples. So here we have two objects, two trolleys A and B. This side is before collision and this side is after collision. Okay, so here you can see the total momentum before collision. That is what we learned. Always the momentum is conserved. So in a closed system, the total momentum of objects before collision equals the total momentum of those objects after collision. Now what is momentum? Momentum is mass times velocity. So when we say total momentum, we have to consider the momentum of this and the momentum of this, add them together. So before collision, the momentum of this plus the momentum of this should be equal to the momentum of this body after the collision. So here what happens is these two things stick together after the collision. So clearly this is an inelastic collision. And we will also see relative speed. Relative speed of approach is equal to relative speed of separation in an elastic collision. But if it isn't, then they are not equal. So we will see the total momentum before collision is what? The mass times the velocity of each of them, right? So the mass is this, velocity is this, so we get that. And the momentum of this is 0 because it's not moving before the collision. So what happens afterwards? The trolleys stick together and have a common velocity of 1 meter per second. All of that is shown in the diagram also. So the total momentum before should be equal to the total momentum after. The total momentum after is 1.6 plus 0.8. Now see here there are three masses, right? This, this and this, but this we can consider as one body. Now after they coalesce or stick together, they, or join also we can say, they are like one body. So the total mass of this is 0.8 times 3, right? That. Then the velocity of this is 1. Now remember the equation for momentum. Whatever is in these green boxes is very important. Make sure you memorize them with understanding, because in the exam they can ask you to write these definitions down. If you try to write it in your own words, you might miss certain keywords which can cost you marks. That's why I tell the students to memorize with understanding. Okay, so we have this. Now you can see total momentum before collision is clearly equal to the total momentum after collision. Always momentum is conserved. Okay. Then perfectly elastic and inelastic. We should now use the correct scientific terms. Perfectly elastic and inelastic. I already explained that. Now we will anyway go through this. So let's say a body of mass m is traveling at a velocity v. Another body of mass m is traveling at the same speed but in the opposite direction to this one. Then if they collide, since the momentum is conserved, then this is what you can have. So here m times v plus m times v, that is 2mv. That is the total momentum before collision. Now the total momentum after collision is again the same, you can see. And calculation for that is also shown. See. Okay, what about the kinetic energy? Kinetic energy is half mv squared. So half mv squared. Then momentum after collision, that is this. Now again the momentum of this, you can see this is the kinetic energy. So kinetic energy of A plus the kinetic energy of B, that is mv squared. Now after the collision also you can find. Now that is what 1, 2, 2 bodies are there. So m times v, m times v. I think they have shown that, see. So the kinetic energy is conserved because this is an elastic collision. That's why in an elastic collision the kinetic energy is conserved. I told you there are certain points you should know. Always in any collision the momentum is conserved. Now the kinetic energy will be conserved if it's an elastic collision, and you have to know those. Then regarding relative speed also, you should know how to identify whether the collision is elastic or inelastic based on the relative speed. So here they tell you momentum is always conserved. Okay, let's see what do we mean by the relative speed. If objects are traveling in the same direction, then we subtract the speeds to get the relative speed. If the bodies are traveling in opposite directions, let's say one is to the right, other is moving to the left, then to find the relative speed we simply add the speeds of those objects, because it's like this now. Let's say you are traveling in a car and there's another car coming on the other lane towards you, so you are going towards that car, that other car is also coming towards you, and let's say both cars are traveling at 50 kilometers per hour. So it will appear as if the other car is moving at 100 kilometers per hour, because you are moving at 50 kilometers per hour, the other car is moving towards you at 50 kilometers per hour. Then you see it as if it's moving at 100 kilometers per hour. So that's why we say if they are traveling in opposite directions, to find the relative speed you simply add. If they are traveling in the same direction, you subtract. Very easy, you can remember that. Okay, so here you can see in a perfectly elastic collision, a relative speed of approach equals a relative speed of separation. You have to know this. Okay, so here you can see before collision, then kinetic energy before collision, then after collision it has stopped. So that is this diagram. Okay, so here the kinetic energy is not conserved because you can see they stick together. Stick together means that it is clearly an inelastic collision, because here you can look at the relative speed. Here it's what? 2v. Here the relative speed is it will definitely be traveling at a slower speed than this. So here what happened? Yeah, so it has stopped. So that's why if it stopped, then there is no kinetic energy. Okay, you can do these questions in the brown boxes for homework. Let's go through another example. Let's go through another example to help understand the theory better. In the game of balls, a player rolls a large ball towards a smaller stationary ball. See, a large ball of mass 5 kg moving at 10 meters per second strikes a stationary ball of mass 1 kg. The smaller ball flies off at 10 meters per second. Determine the final velocity of the large ball after the impact. So let's call that V. Calculate the kinetic energy lost in the impact. Okay, let's see. So we can sketch diagrams like this. And this you can see 10 meter. You can add everything to the diagram. And you can see a stationary ball. So here you can write U equals 0. Okay, now let's find what V is. Very simple. You may have seen this in the O-levels class if you had learned momentum. Those students who are Edexcel students, they learn this. Cambridge students didn't have that in their syllabus, but anyway now the syllabuses are changing. Okay, so here what is the momentum? 5 times 10. What is the momentum here? 0, because the speed is 0. So m is 1. But V is 0. Then what about this? It's 5 times V. Remember, we are using the momentum equation. Momentum is mass times velocity. So mass is 5, velocity is V. We can call it V because we need to find it. Then 1 times 10, 10. We get then V equals 8.0 meters per second. Using the principle of conservation of momentum, set up an equation and solve for the value of V. Okay, so we learned that total momentum before equals total momentum after, and we did that. Now what about this? Calculate the kinetic energy lost in the impact. Kinetic energy equals half mv squared. So half mv squared. M is 5, v is 10. So here this has no momentum, no kinetic energy, it's not moving. So the kinetic energy of that is 0. Then here also we can find the kinetic energy because we know v. So half m v squared plus half mv squared. So we get this. Now here you can see this is 210. Here in the beginning we had 250 joules of energy. So what happened to that 40 joules? It is the kinetic energy lost in the collision. This lost kinetic energy will appear as internal energy. The two balls get warmer, and as a sound energy we hear the collision between the balls. This lost kinetic energy will appear as internal energy. The two balls get warmer, and as sound energy we hear the collision between the balls. It can cause the balls to get warmer, and also part of the energy here, 40 joules, is the sound energy also, we can say. Alright, so you have to do these questions and check the answers in the back of the book. Okay, the next topic under momentum is explosions and crash landings. So here you can see fireworks. These exploding rockets produce a spectacular display of bright sparks in the night sky. Okay, so how we can apply? Now again here is another question. The rock and the earth gain momentum in opposite directions. So if this comes in, the earth is also supposed to go that way, right? But why doesn't it, I mean it moves, but why it's such a small value? Because you will see in the calculation. Okay, so first we will see total momentum of earth and rock equals 0. So we can just hold it and release it. And the earth we can also say is not moving, like we see it's not moving, right? The way we see it from at this level as a person, we don't see the earth moving, but actually it is moving. Okay, so mass of earth, now we can use the equation. Total momentum of earth and rock equals 0. So it's 60 times 20 plus 6 times this thing, and it should be equal to 0 because the total momentum before equals total momentum after in a closed system. Then we can get V, and this means it's opposite to this direction because we took 20 as positive down. This should be up. So you can see it's moves, but you can see this is very small value, and that's why they say this. The earth moves very slowly indeed. In the time of the rock's fall, it will move much less than the diameter of the nucleus of an atom, because the earth is massive. This is only 60 kilograms. So far we saw momentum in one dimension, that is momentum you can say in a straight line. Now we will see momentum or collisions in 2 dimensions. 2 dimensions means like a surface, 3 dimensions means a region. So for example, if we take the example of a train moves along a straight railway track. So that is 1 dimension because the train can either move forwards or backwards. It can't move sideways. Now if it is 2 dimensions, then it can go, in addition to forwards and backwards, it can move to the left and right, sideways it can move. Then the third one, or the third point is is 3 dimensions. So if it's in 3 dimensions, in addition to it moving forwards, backwards like the railway track, it can also move sideways like a car now, and that is the helicopter, right? Because the helicopter can move forwards, backwards like a train in 1 dimension. It can also move sideways in addition to moving forwards and backwards like a car. It can move sideways, or if it's a car, it can move sideways. So that is on a surface, that is 2D, and the other one is 3 dimensions. 3 dimensions is sideways, forwards, backwards, and also up and down. It can move up and down. Okay. So example, helicopter, right? It is rare that collisions happen in a straight line in 1 dimension. So okay, so here is example. You can see here, this ball collides with this. This goes that way, this ball goes in the other direction. Alright, so here you can see what happens. This thing is shown here. So what happens in the beginning, only the white ball was moving, then the red ball was stationary. Now after colliding, the red ball moves that way, white ball moves this way. So remember, when you learned vectors, you learned that the length of the arrow is proportional to the magnitude or size of the vector. The direction of the arrow, vector arrow, indicates the direction. Okay, we have that here. So you can see this length, and look at this third length, it's much longer. So what did we learn? The total momentum before should be equal to total momentum after. And if that is, remember, this is, we can do it as a vector addition like this. As long as we don't change the direction of the arrow, the direction of the vector, that is, it won't then means they are equal vectors. If they are the same length and the same direction, the two vectors are equal. Now when that happens, and since this is a perfectly yeah, I think they have assumed it's a perfectly elastic collision, right? Yeah, also we can say if it's a perfectly elastic collision, then we can do something like this. Okay, so that means we assume there is no friction on the floor, and then you will get something like this. So what is this? This is where we join the tail of one vector to the head of the other vector, or the nose or tip of one vector to the end of the other vector. So we don't change the direction, we leave the direction as it is. Okay, you can see here. Then this we have it this way, this we have it that way. Okay, another example. Okay, let's go through this example also. A white ball of mass m equals 1 kilogram. Okay, so the mass is not shown here, and it's referring to this diagram. Okay, we can sketch a diagram like this also. Moving with initial velocity speed of 0.5. Okay, that also you can label. Meters per second, collides with a stationary red ball. Stationary red ball, so that also you can add to the diagram. Of the same mass, they move off so that each has the same speed, and the angle between their paths is 90 degrees. What is their speed? So they move off so that each has the same speed. So here the speed is the same, and they are also telling you angle between the paths is 90 degrees. What is their speed? What is their speed? Okay. Okay, so draw a diagram to show the velocity vectors of the two balls. Now here this speed and this speed are the same. So white ball this way, velocity vectors for the white and red balls. Because we know that the two balls have the same final speed v, their paths must be symmetrical about the y direction. since their paths are at 90 degrees to one another, each must be at 45 degrees to the y direction. Okay, so then we have this. We know that the momentum is conserved in the y direction, hence we can say, okay, now here how do we know that each of this is 45? Because it's the same speed and also they have the same mass. So that means because the angle is 90, that means the angle here should be 45, because they have the same mass and the same speed after the collision. Always the momentum is conserved. So if you take the momentum in any direction, in a particular direction, the total momentum before in that direction should be equal to the total momentum after in that direction. We know that momentum is conserved in the y direction, hence we can say initial momentum of the white ball in y direction equals final component of momentum of white ball in y direction plus final component of momentum of red ball in y direction. So that is in this direction we take. So we resolve this way, resolve this way, that should be equal to this. This is easier to understand using symbols. mu equals mvy plus mvy, where vy is the component of v in the y direction. The right hand side of this equation has two identical terms, one for the white ball and one for the red. We can simplify the equation to give this, and then we can find v. This goes off, and also u was already given, right? Yeah. Yes. So mvy, but vy is what? V cosine 45. So we get that. So each ball moves off at 0.354 meters per second at an angle of 45 degrees to the initial direction of the white ball. You can write a final statement like that. Okay, another example. Figure 6.17 shows the momentum vectors of particles 1 and 2 before and after a collision. Now show that the momentum is conserved in this collision. Now in the beginning, particle 1 is moving. Momentum vectors, particle 1 has come from the left and collided with particle 2. So particle 2, consider the momentum in the y direction before collision is 0 because it's moving in the x direction. Because particle 1 is moving in the x direction and particle 2 is stationary. So here you can see after collision, component of momentum of particle 1 is 3 cosine. Now that is in the this we have in the x direction. Okay, after collision, so 3 cosine 36.9, that is that upward. Okay, now in the y direction. Okay, here we are doing in before collision in the y direction it's 0 because everything here you can see before collision is moving in the whatever was moving in the x direction. Okay, now what about y direction? Here this is 0, here it will be this cosine this, then this cosine that. But remember, this is up, this is down, and momentum is a vector, so you need to consider the direction. So that's why they say here upwards, here this one downwards. Their components are equal and opposite, and hence their sum is 0. See, before collision in the y direction it's 0, so after collision also always I told you the momentum is conserved. After collision also it's 0. Hence momentum is conserved in the y direction. Consider momentum changes in the x direction. Before collision, momentum equals 5 kg/m per second to the right. After collision, okay, so we can consider in the x direction also now. See, so you can take sine of this, which is the same as cosine of this angle here. So 3 sine 36.9, 3 cosine 3 sine 36.9 or 3 cosine of this angle here. So that is what, 53.1. Now here also we can do the same, 4 sine 53.1 or 4 cosine this angle here. So they are using cosine. Then 90 minus this will give you that 36.9 to the right. Total momentum to the right is, you add these two, and that should equal the total momentum before the collision. Now you can see that also. So that is 5. It's given in the diagram. Okay, so when you add this and this, you get 5. An alternative approach would be to draw a vector triangle similar to figure 6.15b. See, in this case the numbers have been chosen to make this easy. The vectors form a 3, 4, 5 right angle triangle. Because the vectors form a closed triangle, we can conclude that momentum before collision equals momentum after collision, that is momentum is conserved. See, 3, 4, this one we can form the 5. So we have to join the arrows, tip of one arrow to the tail of the other. So let's say without changing the direction or the length. So without changing direction and length, we can draw this vector here. And this one, that same length, we can do it there. So you will have that momentum before collision equals momentum after collision. Momentum is conserved because it forms a closed triangle. So that means the momentum is conserved. Alright, the last topic is momentum and Newton's laws. You have to know the 3 laws. Newton's first law, second law, third law. You can see here, what is the Newton's first law, what is the Newton's second law. Another way of saying Newton's second law is this, and also this. So you can see it's all under topics. Newton's first law: an object will remain at rest or keep traveling at constant velocity unless it is acted on by a resultant force. So this is the Newton's first law, you should know it. The Newton's second law, we can say the resultant force proportional to the rate of change of the linear momentum of that object. Okay, resultant force and the change in momentum are in the same direction. Then here also we can say the resultant force acting on the object is equal to the rate of change of its momentum. So here it says equal, here it says directly proportional. So here proportional, here afterwards equal. So the constant of proportionality is equal to 1. Okay, so both ways we can say the Newton's second law. And even this is the Newton's second law. So you can study all 3. I think the best would be to write this one. Okay. And here is an example to help you understand it better. Calculate the average force acting on a 900 kilogram car when its velocity changes from 5 to 30 meters per second in a time of 12 seconds. Now we can use this equation. Also I have created a video on this Newton's laws, a separate video. You can watch that for a detailed explanation. Okay, so we can see the change in momentum over the time is the rate of change of momentum. The change in momentum is what? 900 times 5 minus 900 times 30, or 900 times 30 minus 900 times 5. So they have shown that here. then 27,000, 4,500, subtract, we get this, and that divided by the time, 12 seconds, so we get that. Okay, that is the answer. Then a special case of Newton's second law of motion, and we have this. So you should know all these forms. Now remember, change in momentum over time. Change in momentum is final momentum minus initial momentum. Final momentum is this, initial momentum is that. We can factor out them, and we have this. So all these forms you should know, because you can get questions where you have to use either this equation, this one, like that. Then also you can see v minus u over t is the acceleration, change in velocity over time, acceleration. So we can write this. Alright, then the Newton's third law. Again, I have created a video explaining in detail the Newton's third law. Simply we can say, for every action there is an equal and opposite reaction, or when two bodies interact, the forces they exert on each other are equal and opposite. Another way of saying this, a detailed way, is when a body A exerts a force on body B exerts an equal and oppositely directed force on body A. That is the Newton's third law. Okay, so here they have given an example. You can read this, I think it's self-explanatory. Okay, now we have come towards the end of the lesson. What did we learn? What is the summary? We will see it here now. Linear momentum is the product of mass and its velocity. Remember, momentum is mass times velocity. We can write it like this with symbols. The principle of conservation of momentum. Now, by the way, this is a question I have seen frequently tested in your exam paper. So make sure you know the principle of conservation of momentum. And I told you, a common mistake students make is they forget to write this part. For a closed system in any direction, the total momentum before an interaction is equal to the total momentum after the interaction. Interaction can be a collision, explosion, like that. In all interactions or collisions, momentum and total energy are conserved. Always momentum is conserved. Always the total energy has to be constant. That means the energies of the bodies before equals that of them after. Kinetic energy, momentum and total energy are conserved. Okay, then kinetic energy is conserved in a perfectly elastic collision. Relative speed is unchanged in a perfectly elastic collision. Kinetic energy is conserved in a perfectly elastic collision. Okay, so how do we say that it is a perfectly elastic collision? One thing is kinetic energy is conserved. That means total kinetic energy before equals after. Then the other way is relative speed of approach equals relative speed of separation if it's elastic collision. In an inelastic collision, kinetic energy is not conserved, and also the relative speed of approach is not equal to relative speed of separation. So what is happening in this inelastic collision? Kinetic energy is transferred into other forms of energy, example heat or sound. Most collisions are inelastic. Most collisions are inelastic. Most collisions are inelastic. And also I told you, if the two bodies coalesce means they stick together or they couple, they move as one body, then kinetic energy is not conserved. It's clearly an inelastic collision. Relative speed of approach is not equal to relative speed of separation, because if they stick together after the collision, then the relative speed of approach is 0. Both are moving together, so it's as if you're on one body, it's as if the other body is stationary when you look at it from the body you're on. Newton's second law of motion, the resultant force acting on a body is equal to the rate of change of its momentum, and then we can write these equations. Newton's third law of motion, when two bodies interact, the forces they exert on each other are equal and opposite. The equation F equals ma is a special case of Newton's second law of motion when mass m remains constant. Okay. Special case. Okay. So we have arrived at the end of the lesson. Make sure you do these questions and check the answers at the back of the book. Now these questions have to be done after doing these questions in the brown boxes. So make sure you do those questions in the brown boxes first, and then you do the questions that are at the end of the chapter. Always check the solutions, check the work after you do a question. Next we will see matter and materials.